Unless you want to. Okay, so now we have Netta's second lecture.
All right, thank you. Good to see everyone again, or as many of you as I can fit on my screen at one time. Okay, so let me, since this was a couple of days ago, which I didn't realize yesterday at 4 o'clock, I was like, oh, I'm going to go lecture now. Okay, so just to remind you of what we talked about last time. So last time, we talked about the holographic entanglement entropy prescription for a static classical bulk. So in a static classical bulk, the von Neumann entropy of the reduced density matrix on a boundary region R is given by the area of XR over 4G, where this is the minimal area surface on a static slice, sigma t, which is homologous to R. And I made a number of remarks regarding the various properties of this. It was remarks 1 through 3. So we'll pick up with remark 4, which, well, and I will first outline the rest of the lecture. So we'll pick up with remark 4, which means that today we're going to begin with a couple of comments / remarks on Ryutakinagi, this classical static prescription. Then I'm going to just very, very briefly outline the so-called derivation of the Ryutakinagi proposal. So derivation is maybe a somewhat strong word, but this is the so-called Lefkowitz-Maldacena gravitational replica trick. We won't go into it in too much detail, but I kind of just want to give you a flavor of how it works. So this is a justification of Ryutakinagi from, put this in quotation marks, first principles. It's not really first principles, but in some sense it's as close as we get in AdS CFT. Then we'll talk about the covariant version, which I'll call V2. So V0 was Bekenstein-Hawking, V1 is Ryutakinagi, classical static bulk, and then V2 is the covariant, still classical, holographic entanglement entropy prescription, which is proposed by Hubini, Rangamani, and Takiyanagi. My suspicion is that's what we'll get to today, but we have a little bit more time at that point, then I'll mention the reformulation of it by Aaron Wall, the so-called maxi-min prescription. My suspicion is that we'll have to wrap that up next time. So we begin with a couple of remarks. So actually, let me ask, are there any questions about last time? Okay. So wrapping up last remarks on Ryutakinagi. Okay, so we need to prove strong subjectivity for this, right? Holographic entanglement entropy should satisfy all of the inequalities of ordinary von Neumann entropy, which means that it had better satisfy strong subjectivity. So this was, if you're counting from last time, this would be remark 4. Strong subjectivity for holographic entanglement entropy. And this was proved by Hedrick and Takiyanagi. The proof method is quite similar to the way that we prove that sort of one surface always lies, a surface lies closer to the boundary whenever it's anchored on a smaller boundary region. It's sort of a subtract and add different portions of the surfaces. And it's actually pretty easy to see it pictorially, so I'm just going to draw it. So maybe use different colors. Okay, so we have some, say, 3 boundary regions. We want to prove strong subjectivity, then we need regions A, B, and C, which are non-overlapping for us. So A, C, and B. And let me draw in a couple different colors, the different surfaces under consideration. We need the von Neumann entropy of the union of all of them, S, A, B, C. So we're going to be interested in this surface, which we'll call 1. We will be interested in the von Neumann entropy of AC. So this surface, which I'll call 2. And also the von Neumann entropy of C. So that's this surface. And the von Neumann entropy of BC. So actually, I'm going to give different names to different portions. This will still be 1. 2 is going to be from here up to here. And then from here down to here, that'll be 3. 5 is going to be from here to there. I would call this 4, and this is 6. So just like before, we're just going to add and subtract different pieces. And we're going to reproduce the strong subjectivity inequality. So where are we going to do this? We're going to say, all right, so SABC is equal to just the area of 1. And SAC is just going to be the area of 2 plus 3. SBC is 4 plus 5. And S of C is just 6. And the crux of this argument, just like the last argument we gave, is to use the fact that we have the surface that actually computes the entropy is going to be the minimal one. So we know for a fact, so minimality guarantees for us that 1 is going to be less than or potentially equal to 2 plus 5. And also that 6 is going to be less than 3 plus 4. And hopefully you'll appreciate the fact that I figured out how to label these so that it doesn't bother you on an arithmetic level. So, okay, so then we say, all right, well, what do we get from this? Well, we can just add them up. Say, okay, well, these two together tell us that 1 plus 6 is less than 2 plus 3 plus 4 plus 5. And then we match these up to these ones over here, which finally gives us S of ABC plus S of C is less than or equal to S of AC plus S of BC, which is indeed the strong subjectivity inequality. So it's very nice, very geometric proof. And one thing to note here is that it really is purely geometric. We didn't actually need to use anything as far as, say, energy conditions about the bulk space-time. And all we needed is that we're working on this slice. This is not going to be the case when we go to the covariant picture. When we go to the covariant picture, what is going to happen is we're going to need to assume something about the dynamics and the energy conditions in the bulk. But at least in the static case, it's pretty nice and simple. Are there questions about this? Okay. All right, so this brings me to remark 5. And this is sort of where things begin to get interesting, if they weren't already interesting, which is a question of global versus local minimality. So we can have multiple candidates for a surface to be computing the entanglement entropy of a boundary subregion. So suppose that we're interested, for example, in the case of 2 intervals in AdS. So we have this is a static slice of AdS. And suppose we're interested in the union of the intervals R1 with R2. And I'll call the remaining pieces just B. So that B is equal to the complement of R1 union R2. Well, we have 2 different candidates for the minimal surface for R1 union R2. We have this possibility, one that hangs in the bulk this way and this way. And we also have one that goes like this and like that. So we have, so let me call this one x1, x2. So x1 is the minimal surface of R1 if we were not even thinking about the fact that there's an R2 in there. And x2 is the minimal surface of R2 if we were not thinking about the fact that there's an R1 in there. And then we have this additional surface y, which is still homologous to R1 union R2, but would not be a candidate surface for just R1 or just R2. Now we want to compute S of rho R1 union R2. So we could compute it from these two surfaces. Emphasize that's these two, that's the homology hypersurface. Or we could compute it from these two, and this would be the homology hypersurface. So we have two different candidate surfaces here for the von Neumann entropy. Now, if it happens to be the case, push this up a little bit. So again, this is x1, x2, this is these two, y refers to both of these. Now, the point is that both of them are local minima of the area. If you slightly perturb either one of them, the change is 0 to first to leading order, but then you keep on changing, you find that it's a local minimum. But only one of these is going to be a global minimum, most likely, unless you're at a very specific point. So if the area of x1 plus the area of x2 is less than the area of y, then x1 union x2 is the Ryuta-Yanagi surface. And this is sometimes the boring case where the Ryuta-Yanagi surface is also the causal surface. So there's sort of nothing interesting here. So far we wouldn't know that there's a difference between the surface that computes the entanglement entropy and the causal surface. But actually, that's not quite right. Because if the area of x1 and plus the area of x2 is smaller than the area of y, then that tells us that S of rho B, which is the region complementary to R1, R2, is going to be given by the area of x1 plus the area of x2 over 4G. So already we can see here that if we're looking at B, so this is B, if we're looking at B, the von Neumann entropy is given not by the causal surface of B, but by this other global minimum. So this is in some sense our first, this is our first concrete example of a situation where the causal surface does not in fact coincide with the Ryuta-Yanagi surface. And this is of course quite generic, but you can even see this already in pure AdS just by picking a couple of boundary subregions that and moving them along, making them larger or smaller, and seeing that there's a transition between it being, so for B small enough, Y will dominate, and as you make B larger, eventually you're going to have this one dominate. Other questions on this? Questions? So this is typically referred to as a sort of a phase transition. The reason this is a phase transition, we call this a phase transition, is that even though the von Neumann entropy is continuous through this, the derivative is not, so you sort of get a kink in it, which is very analogous to, that's sort of how we think of a phase transition. It's one way to think about it. And what's going on here is that you can think of the density matrix rho R1, R2 as essentially factorizing to leading order in G Newton in the case where this dominates. So if x1 union x2 is the Ryuta-Yanagi surface, then we expect that rho R1 union R2 factorizes between R1 and R2 to leading order in G. Keep in mind, this is everything here is to leading order in G. And as we make the region progressively larger, eventually it's not going to factorize even to leading order in G. So this is sort of the physics that's going on here. Now, I want to emphasize the fact again that it's very generic for the causal surface to not coincide with the Ryuchakinagi surface. And even though this is sort of the first example we've seen of it, that's typically what happens. So, any questions on this? The audience is being very quiet. Either everyone already seen this ad nauseum, or nobody understands the word I'm saying. Yeah.
So you're saying that the Hilbert phase of R1 union R2 factorizes, and from a gravitational point of view, it means that I guess it means that the degrees of freedom inside those regions enclosed by x1 and x2 factorized from the rest of the space-time?
Approximately.
But approximately, okay, so it's
yeah.
not a statement that quantum gravity factorizes, it's a statement that it factorizes at a leading order, right?
Yeah, it's very important to keep the leading order here. If you try to make it factorize exactly, then you run into all kinds of contradictions. I mean, you're talking about a quantum field theory here is not going to factorize exactly between these two intervals. So yes, approximately to leading order in G, things will factorize, but that statement is not precise, and it's very important that it's not precise. Other questions?
This may be a question better for after the lecture, so do let me know if that's a better. But is this related to like the solutions like the black funnel and the black droplet solution and those kind of phase transitions, or is this just an unrelated phenomenon?
It's a somewhat different phase transition. So I'm going to give a 30-second answer, and then we'll talk about it more after the lecture. So the black funnel versus the black droplet is an exchange of dominance, those kinds of transitions are an exchange of dominance in the solution to the Einstein equation of the space-time, which one is the sort of dominant saddle in the gravitational path integral. And while you can think of this as an exchange of dominance also in the gravitational path integral, and we're going to talk about that very shortly, it's not an exchange of dominance in the sense of what the bulk actually looks like, because the bulk doesn't change. It's an exchange of dominance in the sort of the replica manifold, which in fact is literally the next thing. Well, okay, it's the next thing I'm going to talk about.
Okay. Yeah. Cool. Thank you.
I agree that the pictures look very suggestively like the black funnel and the black droplet. Yeah. Other questions? Okay. So I'm going to suggest an exercise to do, which is kind of fun. You can do it analytically. So suggest an exercise. So one thing you can do is compute the phase transitions in AdS Schwarzschild. So the idea being you have two intervals, and you take one of them can be the entire, say, left asymptotic boundary, and one of them is just a piece of the right, but they're both two pieces of the right. You can play around with this, and what's actually kind of fun about this is if you start out just on the right and you take progressively larger single region, then and then you start adding more and more pieces on the left, you recover something that looks like the page curve for those of you who are familiar with the behavior of unitarity of one-element entropy. So this is an example of as you take more and more subsets of the system, eventually it begins to purify itself. So if you sort of play around with two intervals, either all of the left, part of the right, part of the left, part of the right, etc. You can sort of recover a page curve as you eventually take everything to be included in your in the union of the two subregions. And I also want to emphasize one other thing, which is this type of transition. You might think that maybe it's special to, so this thing here, you might think, oh, maybe that's kind of something that's special to two intervals, this type of jump between surfaces. And it's really not. So you can have this happen just with one interval. And an easy example of that is something called the AdS soliton, which is a type of geometry that you get by analytically continuing, sort of wick rotating two directions of the black holes. So, so I guess I could say look at phase transitions in the soliton, AdS soliton. So that's an example where you take one interval. This thing is caps off smoothly at some finite radius, and you take a single interval and you make it progressively larger, and eventually the Ryutake-Nagi surface just ends up just becoming that hugging along that particular the smooth cap of the space-time. So that's just something to play around with this. All right. Are there any additional questions? I'm going to make one last comment on the geometry of these surfaces, and then we're going to move on to justification of this from the path integral. Okay, so remark 6, which is the last one. So in general dimensions, looking for the minimal area surface on some Cauchy slice means that you want to find a local minimum on a given Cauchy slice, right? So you have some Cauchy slice. So you have this topology and you have the metric. So gamma here is the metric on your Cauchy slice. And you have some surface sigma. It has some normal on the Cauchy slice. And of course, the Cauchy slice has a time-like normal to everything. So we have the surface sigma, and there's some induced metric H on the surface sigma. We talked about this last time. And here, both of these are normalized, this to -1, and this is normalized to 1. So the area of sigma is given by the integral of the infinitesimal area element on sigma. And if sigma is to be a local minimum on our Cauchy slice, capital sigma, then we must have delta of the infinitesimal area element, as we imagine slightly deforming this, delta NA equals 0. Meaning, as we slightly deform the location of the surface to first order variations will not change the area. That's what we mean when we say this is the local extremum of the area functional. So another way to write this in terms of the more natural geometric quantities is the Lie derivative. And again, if this is sort of not something that you're super familiar with, it's not very important. It's more to give a little bit of geometric intuition on this. But the point is that you can write this as just the Lie derivative in the n direction of this infinitesimal area element equals 0. So this is an identical statement, and which, just to be complete, you can also write as 1/2 HAB, the Lie derivative of HAB equals 0. Now, the important thing that I want to emphasize here, that I'm going to get to, is that if you use the fact, so using, I guess you can say exercises to show this. Now, using the fact that that sigma is static, which is telling us that this covariant derivative of this t vector is 0, you can show that this quantity is actually equivalent to demanding that this be a local minimum of the area. So these two equations are identical. So this is another way of writing down that this thing lives on the static Cauchy slice and is a local minimum. And this is going to be much more useful for us for the covariant formulation, where again, H here is the metric on the surface sigma. One thing you can also note when you see this is that the only way in which you use the fact that sigma is static is in this equation here. So but it turns out you don't actually need sigma to be static. You just need sigma to satisfy this. You don't need space-time to be static. You need to have a Cauchy surface that satisfies this. So this is called a sort of moment of time symmetry. So the actual statement of Ryutakinagi is a little bit stronger than I originally presented it. You don't need the spacetime to quite be static. You can also have one of these surfaces, which are moment of time symmetry, or equivalently also called totally geodesic. And if you have that, then you can basically, you can do everything that you do in the static case. All you really need is this equation over here. So Ryutakinagi is just a little bit more general than I made it out to be originally. And again, this formula is one that we'll use a decent amount.
Netta?
Yes.
Could I ask a quick question about moments of time symmetry? So this condition is purely local. I think it's equivalent to the extrinsic curvature of the slice vanishing.
Yeah, exactly. As a tensor.
As a tensor, right? Not just as a trace.
Mhm.
So we call it a moment of time symmetry, which makes sense because
No, it doesn't. It doesn't make sense actually.
well,
I think I know what you're going to say, but go ahead.
it makes sense locally. The thing is, you'd sort of want to say that this implies that the entire space-time is time symmetric, that the evolution of the space-time going forward from here is the same as the evolution going backward from here.
Yeah, that's not true. It's not the case.
Right.
Yeah. So we call this a moment of time. Sorry, I keep interrupting you. Go ahead.
Well, my question is, if that's not the case, right?
Mhm.
If the space-time is not globally time symmetric, but locally time symmetric,
Yeah.
then how do we guarantee that all of the extremal surfaces lie in the moment of time symmetry? It makes sense if you have a Z2 symmetry of the space-time, because then uniqueness would fix them to lie in the fixed point of that symmetry.
Yeah.
But otherwise, it seems a little complicated.
Good question. Yeah. So so indeed, this does not have to be a moment of time symmetry, and you can have examples. For example, in AdS FRW, where you have these types of surfaces that have totally geodesic hypersurfaces, and it's a cosmology. And in fact, these surfaces are not moment of time symmetric at all. They're not sort of. I mean, it's a Big Bang, Big Crunch, but this surface is not the one that goes to t equals 0. So that's a really good question, but you need not worry. So Aaron and I actually proved that if you have a surface that actually touches this at any point, if it starts out being tangent to it, if you have an extremal surface that starts out being tangent to a totally geodesic slice, it remains at that totally geodesic slice for all time. So you can actually prove this. The way that you prove it is a little bit, so it uses a theorem that I will mention briefly that you are probably familiar with, which is the tangency of surfaces with different values of the trace of the extrinsic curvature. It's a little bit more complicated here because you actually need to use the full power of the total geodesic. Now, the reason these surfaces are called total geodesic is because it was known for it's been known for a long time now that anytime a geodesic is tangent to it, it remains on it. But it actually turns out to be also true for extremal surfaces in general. So, so yeah, that's a very good question. It does turn out that it's actually fine, and you're actually okay even if you have these without moment of time symmetry, without a Z2 symmetry in time.
Then I guess the AdS equation at the boundary tells you that the tangents at the boundary need to lie in the moment of time symmetry.
Exactly, and that's as long as you work in the conformal completion, that's exactly enough.
Okay, so you could worry that if you're looking at the extremal surface of a boundary region that is an entire asymptotic boundary, then you would not be able to use that same principle.
That's right, and it may indeed be the case that that surface does not lie on the moment of time symmetry. The important thing for Ryutakinagi is that if your boundary interval is essentially defines one of these slices for you, then the corresponding surfaces will lie on it also. But if you have the entire asymptotic boundary, it doesn't define a particular choice of Cauchy slice for you. And so I think it's fine in that case if the extremal surface happens to not lie on the Cauchy slice, on that particular totally geodesic Cauchy slice.
Cool. Thank you.
Other questions?
Yeah, I have a follow-up.
sorry.
Oh, sorry. Yeah.
Go ahead, Osman.
Okay. Yeah. So this thing you and Aaron proved, does it rely on like deforming the RT surface gradually and it not jumping, or does it like also
Yeah, so this is it's an equation. Yeah, good. So this the theorem is it does rely on this deformation. So it actually tells you that it doesn't matter whether this surface is a global minimum or not. Any local minimum that starts out on this will remain on it.
Oh, good. Yeah.
Yeah. Was there another question?
So just a very basic question, but the RT formula, like we have to specify the sigma for it, and that's why we aren't we don't care about the variations in the t direction?
Yes, although one of the reasons that I like to introduce it at this point is that this is the formula that we will end up using when we don't care about the Cauchy slice either. So, but yeah, that's right. When you sort of already specify the Cauchy slice, so you already know the variations in the t direction are not important. And I mean, in fact, this is identically 0. Other questions? Okay. All right, so we're now going to do a sort of lightning review of, or lightning preview, or whatever you want to call it, overview rather, of how we justify this, the Ryuta-Yanagi formula from quote unquote first principles of AdS CFT. Now I'm going to issue a huge disclaimer here, which is that this is not rigorous. There are a lot of steps that are kind of shaky, and I'm not even going to go into a lot of detail. But what is important to me is to make sure that you have the general idea of where this formula, how this formula can be, in some sense, motivated or argued from more fundamental aspects of AdS CFT. Because at this point, the way it stands right now, it's really just a conjecture. So we want to put it on a somewhat firmer footing. Okay. So justifying the Ryuta-Yanagi formula. Okay, so the question is, can we derive RT from more basic principles of AdS CFT? Now, in some sense, the most basic principle of AdS CFT is Z AdS equals Z CFT. That's kind of as basic as it gets. So can we derive this from starting out from these equivalents of the partition functions, or given that this is a classical formula, from the equivalence of ZCFT with some saddle point approximation of the gravitational path integral, e to the minus the on-shell gravitational action. So derive, as I mentioned, it's kind of a strong word for what we're going to do, but I would say strongly motivate is maybe the correct term here. So this is an argument due to, so I should have said over here, this is Lefkowitz and Maldacena. And it has been generalized beyond the static classical case to include all kinds of corrections, to include dynamics. I'm not going to talk about it in those more general cases. I just want to give you a flavor of how the argument is supposed to work. And for that, we can just work in this static classical case. So how does the argument work? So let's consider a boundary state. Consider a boundary state, rho r. And we're going to consider states that are prepared from a Euclidean path integral. So prepared by Euclidean path integral. So we could represent it pictorially as something that sort of looks like this. So you have some cut R and another cut below it R. So here we've glued together the complement of R over here, and we've left open this this cut. So the idea being that from the Euclidean path integral, you can compute any expectation value or any transition function between, say, some state on R and some ket on R and some bra on R, just by putting them together with this cut here along R. So, okay, we have some state in the CFT. It was prepared in this way. Now, we're not necessarily sure, not necessarily the case that this is normalized. So let's normalize it. So I'm going to drop the R. It's always going to be with R. Just we'll make it a little messier if I keep it there. So we'll define rho hat. This is the normalized state. It's just going to be rho over trace rho, since the gravitational path that are going does not have to give us a normalized state. And we want to compute S of rho hat, which of course is minus trace rho hat log rho hat. And this we can represent using the so-called replica trick. This is just a trick for rewriting this. Limit as n goes to 1 over 1 minus n log of trace rho to the n. So again, this is just a computational trick, which is incredibly useful, maybe more useful than it has any right to be. And in terms of the unnormalized state, we can just write this as 1 over 1 minus n log of trace rho to the n over trace rho raised to the power n. Okay, so we haven't done anything with AdS CFT yet, but we are getting there. But first, I want to just mention how we're thinking about the replica trick here, because it's going to be very important. The boundary geometry is going to be very important for the bulk. So we define, again, I apologize, this is a review. We define this sort of replicated partition function, z sub n, trace rho to the n. And this is pictorially, this is a partition function on n copies of this boundary geometry that is cut sort of and identified. So I'm going to draw a picture for that. So we have this is a partition function on this boundary geometry, which I'll call b sub n. Draw multiple copies of it. And here we have our cut R. So I'm going to, so here we begin on one side of R. And this is going to be identified with the other copy with this top of the cut. The bottom of this cut is going to be identified with the top of this cut, and so on, dot, dot, dot. And then this one is going to have an n minus 1 and an n, and then it will be identified here with this n over here. So z sub n is just going to, this is the sort of the replicated manifold that we're going to be thinking about. And I use B here just to remind you that this is, at the end of the day, an asymptotic boundary, and we're going to be interested in finding the bulk dual to it, the bulk solution for that. So now we can write the von Neumann entropy, again, using the replica trick. So S of rho hat, it's going to be the limit as n goes to 1 over 1 minus n, log of z sub n over z1 raised to the power n. Okay, now we're going to use the fact that we're working in the semi-classical limit, and we're also going to use the fact that we have a static spacetime, which means that we have we can talk about the Euclidean continuation of it just by taking this distinguished t coordinate to I tau. So in the semi-classical limit, this classical static limit, z sub n is going to be approximately equal to e to the minus I b sub n, where I here is the on-shell Euclidean action of a gravitational saddle. I'm going to write this down. So I of b sub n is the on-shell Euclidean gravitational action of a bulk saddle, which we'll call Mn Gn, with boundary b sub n. Okay, so this is where we use the sort of first principles of AdS CFT, the ZCFT equals Z AdS. And the reason that we are able to take this approximate thing here, the reason that there's no complication in taking this to be the Euclidean action, is because we're working both in the classical limit and in this Euclidean, in the static case, which means we have a Euclidean continuation that we can easily take. Any questions so far?
Is the adjective on shell describing the action? Is that supposed to communicate something more than the fact that it's a bulk saddle?
No, I should have really just said this is the Euclidean action for a bulk saddle, meaning on shell.
I see.
Other questions? By the way, let me know if the page is moving too quickly if you're trying to write stuff down, and I'll just bring it down quite more slowly. Okay, so in this approximation, we have S of rho hat is going to be, so we can rewrite it as partial n I of b sub n minus ni of b sub 1. This is just the usual boundary evaluated at n equals 1. So a good exercise to do if you don't trust me on this is to just do the arithmetic or the algebra out yourself. It's not very complicated. And the obvious thing that is concerning at this point is that n clearly has to be, must be non-integer for us to take a derivative here. But so far, of course, we've had this discrete integer number of copies. So clearly, we're going to have to do something different in order to, we are going to have to think about n as a non-integer somehow. Now, another couple of things to note. So 2 things to note. So the first is that b sub n is singular. Right, along the edges of the cuts, we have this. We have a singularity in this manifold as we identify it cyclically. A second thing to note is that b sub n has Zn permutation, cyclic permutation symmetry. So one thing that is a very natural question to ask at this point is, are both of these also true? Are these also true of Mn, the corresponding bulk geometry? And the short answer is no, and that's important. So the first one you can ask, is Mn also singular? And the answer is no, because we get a smooth evolution from the Einstein equation. So we start out with this singular geometry, but as we evolving towards the bulks immediately gives us, it smooths it out. So that's the first thing. So that's good. We prefer dealing with smooth things than with singular things. Now, the second is not necessarily. So this Zn cyclic symmetry, it's typically called this replica symmetry. There's no obvious reason why the bulk actually has to also be replica symmetric. In principle, it's possible that the bulk would be breaking the replica symmetry. We are going to assume that it is replica symmetric, that the symmetry of the boundary is inherited by the bulk. It's interesting to ask, when that is not true, and what does the failure of that assumption mean? But that's a sort of a higher order correction, not literally. That's a correction to this formula that we're not going to deal with. So so this is not necessarily, but we'll assume so. So we assume this anyways. This is typically how it's done. Again, this is very far from a proof, but it's a really good argument. Okay, now even if we assume that we have the symmetry in the bulk, that doesn't mean that we don't have fixed points of the symmetry. Symmetry doesn't have to act smoothly, and so the bulk might have fixed point. So we'll assume so. Of course, bulk could and really should have fixed points. So what we're going to do is we're going to quotient out by this Zn symmetry. So we're going to define a quotiented geometry, M hat. This is going to be Mn quotiented by Zn. And the reason that this is a nice thing to do is that it puts so over here we have the action of Mn and the action of M1. And quotienting out means that we have the same boundary for both of them. So that sort of puts them on an equal footing, which is one of the reasons that we do this. It's very nice to not have to worry about n boundary terms here, about n boundaries here and about just one boundary over here. So, okay, so now we have I of Mn is n I of M hat n. So S of rho hat is going to be the limit as n goes to 1 of n over 1 minus n, I of M hat n minus I of n. So again, these are now evaluated on the same boundary. Okay, so now I'm not going to go into nitty-gritty details, but I want to just kind of sketch out what's happening here. So what we do is we identify the fixed points in M hat. So first we identify the fixed points under Zn. Call this Xn. A very natural way to think of Xn is sort of the extension of the boundary of R from the Bn manifold into the bulk. So this is how we like to think about Xn, is this natural extension of partial R, of the boundary of R, into the bulk. And that motivates thinking of Xn. So this Lefkowitz-Moldesino assumed that Xn is codimension 2, D minus 2 dimensional. Because we think of it again as the extension of partial R into the bulk. So partial R is codimension 2 in the boundary. So we expect that Xn, which is its extension into the bulk, is codimension 2 in the bulk. Okay, so now we have our quotiented manifold, and we have, maybe let me draw a picture here. So we have this R, and we have the Xn over here. And this geometry will have there'll be some directions that are along Xn, and there'll be some directions that are transverse to it. So there'll be some direction R, which is transverse to it, and there'll also be the Euclidean time coordinate. So in order to have the original manifold Mn be regular, we have to have M hat n be a conifold. And the conifold is going to be so M hat n. So Mn is regular implies that M hat n is a conifold with an opening angle of leave 2 pi over n. So we have a conical defect for this in this M hat n geometry. And now the beauty of this, what we went through all this pain, is that now we can forget about the fact that n is an integer at all. We just have some conifold, it has some opening angle, and let's just take n to be real. Any real number, any positive real number, and that's totally fine because we don't need it to be an integer anymore in this picture. So that was the point of going through all of this effort to get this conifold geometry. So now forget about the fact. So now forget about n being an integer. Just take n to be real. You have some geometry with a conical singularity. It's the conical defect is parametrized by this real parameter n. And then what we do is you check out the dynamics. And you find that the equations of motion imply that HAB del A NB. So this here is the normal to the surface within the Cauchy slice, or within, well, it's the normal to the surface on xn, the normal which is not tau. This is 0. And this is precisely our minimality condition. So what we then do is we say, okay, we're going to evaluate the von Neumann entropy. So evaluate the replicatric von Neumann entropy as of rho hat on a so-called smoothed out conifold, a regulated conifold. There are a couple of different ways to do this. Lefkowitz and Maldacena originally sort of smoothed out the conifold, and then you go very, very close to it, and you find that there can't be any counter terms at the conical singularity. There can't be any boundary terms at the conical singularity. There's a sort of maybe nicer approach by Xidong, which just adds the boundary terms and then finds that they vanish in a first variation, and so they don't actually contribute, but you add them and then subtract them, and it turns out you get an area piece from that. The long and the short is that when you evaluate this on this sort of smoothed out conifold, you just smooth out the tip, then you basically just get the area. So get the area of xn. This is in the n goes to 1 limit. So as long as you sort of added the boundary terms correctly, or if you've just smoothed out the conifold correctly, then what you get when you actually evaluate this formula, this right here, if you evaluate this, is the area of this fixed point surface over here, which is the minimal area surface. That's required by the equations of motion. So this was in follow-up work by Hale, Hartman, Marolf, Maxfield, and Rangamani, I think. Then they looked into the homology constraint. So you might ask, okay, well, there's homology. We found minimality, local minimality, and we found the area. Where's the homology constraint? And I believe that they found that this surface xn satisfies the homology constraint whenever you can actually construct the manifold Mn for any n. So the homology constraint is in some sense folded into this. So this is sort of implicitly requires homology. Now, I apologize for how lightning review this was. I will emphasize this is not super rigorous, but it has been made more elegant by follow-up constructions. That said, this is the basic gist of it. There's some not so nice work that has to be done when you're evaluating this on the smoothed out conifold, but it's not so bad as long as you have the general idea of what's going on. So I went through this whole derivation with no questions, but let me ask if there are questions about this. Questions?
Could you just
go ahead.
provide, it's a really simple question. Could you just provide some of the references when you put up your notes?
Absolutely.
Yeah.
I will make a blank space right here.
Great.
And when I upload these, I will put references there.
Thanks.
I mean, the obvious one is Lefkowitz Maldacena.
Okay. We'll start
That's
there.
the original reference. But there are a lot of follow-ups that write it up in a way that's somewhat easier to understand. So I will add those as well.
Okay, thank you.
Hi, it's just to make sure I got the idea behind the derivation, because initially we were just thinking about the boundary theory, about the BNs and the ZNs from the boundary point of view.
Yes.
But at some point you introduced the bulk manifold.
Yes.
So is the idea that we're trying to evaluate I of Bn via a bulk calculation?
Exactly. Yeah. So
Okay.
the idea, let me bring up that particular page back. Yeah. So we wrote out this. So we have this formula here. So this so far we've done nothing involving AdS CFT. This is just pure field theory. now we're going to say, okay, Z AdS equals Z CFT. And that allows us to evaluate this quantity using a gravitational quantity instead. And the gravitational quantity would be Z AdS, except we're working in a classical static approximation, which allows us to, instead of having to evaluate a path, is this gravitational path integral over all possible path integrals, including off-shell contributions and so on, it allows us to just make a saddle point approximation, which is where this comes from. And so
I think I was just confused because here it seems like Bn is the data and then you have the bulk action, but then at some point you switch to Mn looking like Mn.
Oh, I think I used poor notation. Thank you. Yes. So yeah, this is poor notation. So this here I mean the Euclidean action, the gravitational action with boundary conditions IBN. Oh, yeah, the boundary conditions Bn. And here I literally meant the action evaluated on Mn. You're right. This is poor notation. I'm going to turn this into round brackets to denote the fact that that these have to be. This is with boundary conditions Bn and not evaluated on Bn. Yeah. Okay. That's a very good point. And I'll fix it with the rest of the notes before I upload them.
Can I ask another question? Maybe a naive question, but is the idea that this derivation basically gives an alternative, sometimes an alternative definition of Ryota-Gainaki surfaces as the fixed points under the replica quotient? And if that's the case, is there a physical interpretation for that?
An alternative derivation is really an equivalent statement. So this set of fixed points, if you just look at the equations of motion, will tell you that it's the minimal area surface. So it's really another way of saying the same thing. Now, if your question is, what is the intuitive interpretation of that other way? I think I'm gonna have to think a little bit about a good intuition behind that. Yeah, let me get back to you on that.
Yep.
Other questions? All right. So that concludes our discussion of the static case. And we are ready to move on to part 3, which is the V2, which is holographic, the covariant holographic entanglement entropy. And again, this is Hubini, Rangamani, and Takianagi. So we want to generalize holographic entanglement entropy beyond the static case because most spacetimes in GR are not static. And in general dynamics, of course, is sort of the thing we're most interested in. So there are many different examples of spacetimes that are non-static, so collapsing black hole, cosmology, even if you take just static AdS and you start throwing stuff in, all of these are examples of cases where we have dynamics, we want to be able to compute entanglement entropy. So how do we generalize? How to generalize to include time dependence? Now, why is this so hard? It's hard because we really relied on that static time slice in our formulation of Ryota-Gainaki. So now we have to ask, okay, we want to let go of the existence of this distinguished family of Cauchy surfaces. Once we don't have time independence, once we have non-trivial time dependence, we don't have this time-like killing vector field that's orthogonal to these Cauchy slices, and we don't have the distinguished Cauchy slices. So what is XR now? Well, some options we could throw out there. Well, it could be maybe it could be the causal surface. We kind of already know the answer to that is no. We could say, oh, it's still the minimal area surface homologous to R. Or we could say it's still the surface with HAB del B HAC equals 0, homologous to R. Now we kind of know this is not going to happen, but either one of these appears like it could potentially be a possibility. But it turns out that 2 is a non-starter. And the reason that 2 is a non-starter is that you can just start out with some boundary subregion R and then imagine that you just boost any surface you start with, make it null. And then it will simply have 0 area, no matter what R is. And we're pretty sure that it is not the case that the von Neumann entropy of every interval is 0. So 1, we already know that's a no. Even from Ryutake-Yanagi, we know there are cases where the causal surface is not the same as the Ryutake-Yanagi surface. So it's certainly not going to be the case when we include dynamics. 2, also no, because we can then take a surface that becomes null and has 0 area. So the natural expectation then is, well, probably then it should be 3, right? So that is indeed the idea. So the proposal is that indeed it is 3. So in a general, classical, we still haven't included quantum corrections. So classical, asymptotically AdS spacetime. That we're going to have to demand satisfies the null energy condition. This wasn't part of the original proposal, but it's possible to find various violations of things like strong subjectivity if you don't demand it. Satisfying the RAB, KA, KB greater than or equal to 0 for null vectors K. I framed it here as a curvature condition, but since we're probably going to be assuming the Einstein equation most of the time, this is just the null energy condition. I just put a T over here, the stress tensor. So in the von Neumann entropy is given by so S of rho R is going to be equal to the area of XR over 4G. And again, this is to leading order in G and in alpha prime, where XR is what was dubbed an extremal surface. That means that in the same formula, in the same sort of language that we had before, so root H delta NA equals 0 for any normal NA to XR. And XR is also going to be required to be homologous to R. And if you have more than one, then you pick the minimal one. So you can have multiple such surfaces, and we always pick the minimal one, the global minimum among the local minimum. Now, this condition, as I mentioned before, and as I left this for an exercise, this is completely equivalent to the condition HAB, that'll be HAC equals 0. These two conditions are identical. And if you want to show it, you just rewrite this in terms of a Lie derivative and then write the Lie derivative out. And it's a fairly simple exercise to show that this reduces to Ryutake-Yanagi on a, if you have a static spacetime and you're considering a static slice. Are there questions about just the statement of Humaniga-Rangamani-Take-Yanagi?
Can I ask a quick question?
Go for it.
So I thought that when you were discussing the static case, the covariant equation also demanded that sigma is static.
That's right.
but we don't assume it anymore here, right?
No.
So why is the equation still valid? Like why can you write the delta square root h delta na as that equation? Because we're not
Very good question. Yeah, no, I understand what you're asking. So before, NA had to be a vector that was confined to the static Cauchy slice. Now we're saying take NA to be any normal to the surface. We're not requiring that it be that it lie on a particular Cauchy slice. In fact, there's also a time-like normal to the surface, since the surface is space-like. So let me draw a picture. So we have some surface. There's our region R. Surface. This is a codimension 2 surface, which means that there are 2 linearly independent vectors that are normal to it. So I can imagine a decomposition TA NA. And essentially what this equation is telling you is that you have to consider variations in any of, let me go further down, this equation, I'm just going to call this RA. This equation says that this has to be true for any normal. And so that what, physically speaking, what that means is that if you slightly perturb the location of the surface in any direction, there's no unique, there's no nice particular direction that's picked out for you by time independence. But so you have to demand that if you vary it a little bit in any direction, then it's a local minimum, or local extremum, sorry. So the first order variations of this surface in any direction will vanish, or the area will vanish. We're not demanding that it be a local minimum. In fact, that's not going to happen, but for all directions. But we are demanding that it be a local extremum. It's a saddle point. It's sort of the same way that a space like geodesic. I mean, this is space like geodesics in 2+1 dimension. So a space like geodesic is an extremum of the length functional, but it's not a minimum. It's not a maximum. It's just an extremum. And it's the same thing over here. And so this n here is not a special vector anymore. It's just anything that's normal to the surface. That's kind of how you make this covariant. You promote n from being the normal one on a static slice to being normal, any normal in the space-time. Does that answer your question?
Yes, yeah, I see it now. Thanks.
Great. Other questions?
If there are multiple extremal surfaces, do we take the one of minimal area, or do we expect
Yes.
them all to be equal?
So if there are multiple surfaces, you take the one with the minimal area. And in very fine-tuned cases, you could have 2 that have exactly the same area. In which case you say, oh, better think about higher order corrections at this point to try to break the degeneracy. Or you could imagine slightly shifting your boundary interval so that it picks one or the other, because that's very fine-tuned.
Thank you.
Netta, you have 5 minutes.
Thanks. Other questions? Okay, so a couple of examples. So examples. So for example, we might consider a black hole that formed from collapse, say the Vidya geometry. So we throw in some thin shell. And maybe we're asking ourselves, what is the von Neumann entropy of the entire CFT? Well, if we think this is a pure state, then the von Neumann entropy should be 0. And indeed, the surface that computes the entropy here of the asymptotic boundary is just the empty set. Another example of a time-dependent geometry is a wormhole, Schwarzschild AdS, but where we threw in some shock waves. So these are now the horizons. So we don't have this very fine-tuned geometric Schwarzschild where these 2 bifurcation surfaces coincide. So in this case, the extremal surface of one boundary, so let's call this scry1 and scry2. So let's call this x. So x of scry1 equals x of scry2 equals x. But x of scry1 union scry2 is the empty set. So this we've already seen before. Now, again, this comes in as just a conjecture, And actually, you can do something similar to Lefkowitz-Maldacena. It's just not as simple because now you have to consider a complexified manifold instead of just the Euclidean one. But there are some sanity checks that you can do and to understand whether this is a reasonable conjecture or not. So what are some of these sanity checks? One of them is something called causal wedge inclusion. So what is causal wedge inclusion? Where does this principle come from? Well, let's remember some property of the von Neumann entropy. Now, typically sanity checks will be things like, I know that this is this thing that must happen to the von Neumann entropy by properties of the von Neumann entropy. So there must be some bulk mechanism that guarantees that this is true. So one thing that we know for a fact is true about the von Neumann entropy is that S rho R is invariant under unitaries acting on rho R, acting exclusively within that are localized to D of R. So suppose that we were able, so let me draw a picture. This is D of R. And we have some XR over here. Now suppose that it were possible for me to turn on some local unitary somewhere over here, and for it to sort of causally propagate and change the area of XR. Well, then I would be able to turn on some local unitary over here and modify the area of this, and therefore modify the von Neumann entropy of XR, or von Neumann entropy of rho R, just by turning on a unitary, a local unitary on D of R. So this clearly cannot happen, which in particular means that it should be impossible for any local perturbation to propagate from the interior of D of R to XR. And very, very nicely, this turns out to indeed be true. Now, the way that you prove this involves, it's sort of an argument that generally makes use of a bunch of concepts in GR, focusing it and so on. But there is one ingredient to it that I'll discuss briefly next time, which is the so-called representative argument. And the reason that I'm going to discuss it, even though it's a little bit nitty-gritty detail, is because it's an argument style that's just incredibly useful for proving things in AdS CFT about extremal surfaces, about quantum extremal surfaces. It's just, I can't even tell you the number of times that I've used this so-called representative argument. So that'll be, we'll start next time with this idea behind a representative of how you can represent a surface that lives on lives on a different Cauchy slice on another Cauchy slice, and relate the areas of those two, and how you can then prove various inequalities like strong subjectivity. You can prove causal wedge inclusion using this type of argument. And that'll probably be some sense the most detailed thing that we'll do. But because there's no real review of it and it's really valuable, I will go through it briefly next time. Okay, so I think that's time up for me, and it's time for all of you to ask questions.
Great, thank you. Questions?
I have a question.
Mm-hmm.
So in Maldacena's derivation of the RT curve, you use that the partition functions of the CFT and AdS are equal to each other, in the sense that they're in the sense that they're equal to each other in a Euclidean signature, and you sort of in section 3 where you were looking at the scenario 2, where you wanted to look at the covariant holographic entanglement entropy.
Mm-hmm.
You said that you could boost the extremal surface and it would eventually be null.
But doesn't that extremal, if you could boost a surface and make it null.
Yeah.
Yeah.
So that relies on the geometry having a Lorentz signature?
Well, you could always boost any surface you want, but in a static geometry, by doing that, you're not respecting the time translation symmetry anymore. You're sort of, by boosting the surface will immediately take you off of the static slice. So Lukowitz-Maldacena is always going to be, is assuming that you've picked your boundary interval to lie on one of these static slices. And so you can always work on this static slice, which means, of course, that the analytic continuation to Euclidean signature is always going to be very simple from that particular slice. Now, if you happen to boost your surface, then it doesn't lie on that slice anymore. And then you don't have any right to analytically continue you don't have any right to continue it to Euclidean signature. You have to continue it to to a sort of a complexified manifold. And it's not that there is no analog of Lefkowitz-Maldacena for the time-dependent case. There is, I think that the proof is by Dong, Lefkowitz, and Rangamani, I want to say. And so they work with this complexified manifold, and they find the right contour. And so you can do it in that case. But if your question is essentially, what is the thing that breaks when you go to the covariant case that means that you have to worry about things like that, it is indeed the fact that you're not respecting the static time slice anymore.
Okay, thank you.
Mm-hmm. Other questions?
Towards the end, you were saying that if I include a unitary perturbation to ER, then it should not propagate all the way to the Liu-Takayama surface. What if I include a perturbation on somewhere on R, the boundary?
So anywhere on D of R, you don't expect it to propagate in. Now, maybe what you're asking is, what if it's literally like on the boundary itself?
Yeah, well, I was thinking anywhere along that line, or along
so anywhere on the boundary of this. Yes.
No, anywhere along R. So that's
So right here.
Yes. Yeah.
Mm-hmm. It's the same story. We don't expect that if you act with a local unitary within D of R, anywhere in D of R, which includes R.
Okay.
Then it should because that's acting on rho R with a local unitary, and that cannot affect the von Neumann entropy.
Mm-hmm.
So we made that argument in a paper with Matt Hedrick, Albion Lawrence, and Mukund Rangamani, which is the paper where we define the entanglement wedge. So I can send the reference if you want the proof.
Yeah, the representative argument, I'm going to present the representative argument for this, which was by Aaron Wall, which is a somewhat different type of argument, but there's an equivalent argument by Veronica and friends that also proves this from a different perspective.
Yeah, I was thinking more, particularly that, I mean, we know that in AdS CFT, we turn on sources at the boundary, and then those sources propagate to the bulk, and then we sort of study correlators in the bulk. So, but what you are describing here is probably not that, right? You're not turning on.
It's absolutely what I'm describing here. So you turn on some operator here, it propagates in. But the thing is, if that operator is not unitary, then we don't care. But if you're turning on a unitary operator, then we know that it can't change the von Neumann entropy. Now, in general, local perturbations, so if you turn on as a local operator, it should propagate causally and locally in the bulk. And so we demand that for a local unitary cannot modify XR, then that also essentially means that you turn on anything that propagates locally is not going to modify the area of XR. If XR is basically what happens is that XR has to live in the region of space-time where there are no causal perturbations that can travel from the interior of D of R to that surface. So if I draw a conformal diagram, so this is D of R. And this is the causal surface C of R. And we would require that XR lives somewhere in this wedge. That would guarantee that no matter what, where you turn on your local unitary, whether it's here where it would propagate this way, potentially also this way, or over here, propagate this way or that way, none of these signals could possibly change anything about XR. It's a consistency condition that we need, and it fortunately turns out to be true.
Okay, so it seems like we saw that when we are calculating the minimal surface, the causal wedge cannot be a part. The causal wedge cannot give the minimal surface, but it seems like here it has to be true in all cases.
Well, so it's possible to have one of these very non-generic fine-tuned cases where the two exactly coincide. And in that case, you're talking about, but that's, so the causal surface is still space-like separated from every point in the interior of D of R. So it's possible for them to exactly coincide, but it can never be the case that this is, over here or inside here.
Okay, okay.
It always has to be outside of it or at most on it, or potentially null separated to it. So it could potentially lie like over here. Oh, no, it can't because of that. Sorry, I take that back. It has to lie either on it or space like separated to it. I feel like I didn't answer your question though exactly.
Well, you kind of did. Maybe I have to think. So I mean, the thing that I'm probably a bit confused about is the fact that I had in mind that this causal wedge thing and the Ryu-Takanagi surface, sometimes they can be so the causal wedge can serve as some surface inside the causal wedge can serve as a Ryu-Takanagi surface, but that's not always true. And
inside, so there is the Ryu-Takanagi surface or the extremal surface is never inside of the causal wedge.
Okay. Mm-hmm.
It's possible for them to coincide for it to lie on the boundary of the causal wedge if it coincides with the causal surface. But in fact, you can prove this. So this representative argument that we'll see next time allows you to prove that there's actually no extremal surface, minimal or otherwise, that can lie in this interior here.
Mm-hmm. Yeah, I think I get it. Yeah, what you're saying. Thanks.
You sure?
Yeah, I think so. Yes.
So do both things coincide in the example of empty AdS?
Yes. Well, for a particular choice of boundary interval. If you choose a sort of a funny interval, then they won't coincide. So basically what's going on here is that this equation that we have HAB, I'm just going to get indices the same so I don't confuse you guys. I want to make sure I always write it out in the same index structure. Where's my index structure here? All right, well, you'll just have to forgive me if it's not the index structure that I wrote before. So HAB del B HAC equals 0. So this equation is the equation of sort of extremality. That's what guarantees for the surface is extremal. And so there's an empty index here, C, and that allows you to contract. You can contract this with any normal vector you want, and that'll tell you the change in area in that particular direction. So for example, if you contract this with T sub C, then it'll tell you the change in area in this sort of in this time-like direction. Now, the point is that for the extremal surface, this is 0, but for the causal surface, this is generically not 0. So in particular, so we define this quantity as called the expansion. I was going to mention it next time, but we can talk about it right now. So the expansion in some direction, let's say a null direction K, is so this is going to be essentially we can think of it this way, delta H delta Ka, which again you can write in terms of this by contracting it with K. This is 0 for an extremal surface, sort of by definition, because the area has to be non-changing to linear order. And for the causal surface, theta K, if K is a future directed null vector, let's say the one that points towards the boundary, then theta k will be greater than or equal to 0, and the equal is non-generic. So you can see that they really generically don't coincide because this very fundamental property has to be true. Now, the sense in which this shows up in things that we're very familiar with is the Hawking area theorem. So the area of the event horizon increases as a function of time, right? So if we think of, so this here is our causal surface C of R. This is just like an event horizon, and this area has to increase as we move forwards in time for the same reason. And so if the area is increasing in this direction, that immediately tells us that this that it can't be extremal, because extremal means that the area is non-changing to first order perturbations. So the thing that's special about certain intervals in pure AdS is that things are so very fine-tuned that the Hawking area theorem is saturated, that the area is actually not increasing along the horizon. And so then that's when it happens to coincide with the extremal surface. But generically, what will happen if you have an extremal surface, you look at the same sort of this k direction here, then because of gravitational focusing, eventually the area will begin with having no, it will not change to the first order, and then it'll generically begin to decrease. Whereas here it will be increasing. So it's only in that very fine-tuned case where, so this is always non-increasing, and this is always non-decreasing. So it's very special when it happens to be the case that neither one of them is actually changing. And that's pure AdS for you. That's the bifurcation surface of Schwarzschild. Sure, I can come up with some other examples. Basically, whenever you don't have gravitational lensing, that's what's going to happen.
Okay, thank you.
But so if you pick, sorry, but I meant to say, if you pick a funny shaped region in AdS, then what's going to happen is you're introducing shear, and this shear, it acts like a gravitational lens. And so that'll result in the expansion becoming positive for the causal surface, and zero, the surface with zero expansion will have to be deeper in. Because picking a funny shaped region will sort of cause your light rays to shear as you fire them off of the boundary.
So I guess related to this question of when the extremal and causal surfaces coincide, I think it was mentioned last time that a condition was like this modular Hamiltonian being local, and then like I guess you can perform reconstruction with it. So in that case, can you show that that would be completely equivalent to like HKLL, which is what you're doing with the causal wedge? Or?
Yes. So the way that argument roughly, well, the argument itself relies on a reconstruction of the entanglement wedge by Faulkner and Lukowitz, which is very similar to HKLL, except instead of using the Hamiltonian, it uses the modular Hamiltonian. Now, when the modular Hamiltonian is local, then it turns out that it actually does end up looking exactly like HKLL. So yes, so if the two coincide, then you can reconstruct the entire region between XR and the asymptotic boundary, which is the entanglement wedge, which we'll finally define next time. And you can reconstruct that purely using HKLL. If there's some gap here, then you can't use HKLL anymore, because HKLL, you can use some variant of HKLL sometimes, but that becomes a little more complicated. Sort of I mentioned in the Q&A last time. In principle, what you can do is you can say, okay, let me use HKLL to reconstruct the causal wedge. And then that tells me that I have some matter that's falling across this horizon. And you could say, okay, if there's matter falling across this horizon, that's kind of what's causing this horizon to focus. And that's why the theta of that horizon is not zero. So then you say, okay, well, I know what this matter is because I did HKLL. So let me, get rid of that matter. And then you can sort of bridge some of the gap between the causal surface and the extremal surface. But so you could say, I was able to reconstruct it because every time you turn off this matter, you can sort of reconstruct more using HKLL. You sort of you say, oh, I know I turn these operators off, then I reconstruct more, and then I know, more about what's going on deeper in the bulk. But there is a limit to how deep that goes, and it does not have to go as deep as the HRT surface.
Thank you.
Excuse me, I have a somehow related to this question, which, if you want, can be postponed to tomorrow and gather something if it's too long or too informal discussion, which is,
By all means, ask now.
yesterday in the lecture, you mentioned that HKLL is now well posed, and you said that you would have commented on that in case we wanted to. So I wanted to ask if you can comment, expand a little bit on that.
On HKLL, yes, I can certainly comment on that. So, what we know is well posed is the Cauchy evolution. If you have some initial data sigma, and you want to evolve it forwards in time with, say, with the Einstein equation. If you want to add boundary conditions, then you can also do some kind of an AdS version, but that's a little bit more complicated. So let's just talk about flat space case, asymptotically flat space. So you have, we're talking about this Cauchy slice. We know we can do this evolution. This is so this was proven. I forget what year this was, but this was proven by Ivan Choque-Bruhar. This is the well-posedness. This was quite a long time ago, sometime in the 70s, I want to say. The well-posedness of the Einstein of the initial value formulation of the Einstein equation. So that's essentially to say you specify initial data on this, and you're guaranteed that you're going to have a unique solution, up to this this horizon here. You're going to have a unique solution there, and the solution is going to exist. Now, that very much relies on the character of the Einstein equation when this is a spatial hypersurface. When we do HKLL, we kind of want to turn this around and do that instead. We want to start out when this is time-like, and we want to evolve it sideways. And that does not have the same character of the equations as the case when the surface is space-like. And so you cannot prove that it's well posed. And in fact, it's possible for it to be, it really is possible for it to be ill posed. There are, examples of equations of the same character that are ill posed. The reason that I would say I sort of think that HKLL is fine, actually, is that there's this theorem called the Holmgren uniqueness theorem that will guarantee for you unique evolution of equations under certain conditions, which it's sort of hard to prove that HKLL satisfy those conditions, but I suspect that they do. That only guarantees uniqueness. It doesn't guarantee existence, but at least it guarantees that once you specify the initial data here, then and if you know that there's a solution, you're not gonna have to worry about having more than one. So, but if you just specify initial data there, you're not guaranteed that it's going to evolve nicely. And I mean, you can also in AdS, you can even worry about something else. You could worry about so it's going to be slightly separate from your question, but you could worry, well, are the boundary conditions I'm imposing here even consistent with what I'm doing here? And there's a very nice paper by Sergio, who's probably somewhere in the audience, and Sergio Hernandez and Gary Horowitz, discussing these boundary conditions here and the consistency with the data that you impose here. So, I mean, I will also say that these are in some sense mathematical subtleties, but they haven't really proven to be a hurdle to think that we do an AdS CFT. In other words, if you sort of assume that it works and it's fine, then we typically make a lot of progress and don't run into issues. So this is an approach that sort of works until it doesn't. But it's good to remember what is and is not rigorously established, because sometimes it can come back and bite you.
Thank you very much.
Okay, so maybe this is a good time to end the recorded part.